Welcome to this explainer. Okay, today we are tackling something that literally powers our entire modern world, electricity. Now I know physics formulas can sometimes feel like a totally foreign language, but here's the secret. Electricity is actually a highly logical system. When we just break it down piece by piece, concept by concept, it becomes incredibly easy to understand. My goal today is to give you absolute clarity so you can master these basics without blowing a fuse.
We're going to master this topic in 5 simple steps. First, the flow, which is electric current. Second, the push, that's Ohm's law. Third, the obstacle, or resistance. Fourth, the pathways, covering circuit types. And finally, the result, which is power, energy, and heat. All right, kicking things off with step 1, the flow, electric current. If we think about our water pipe analogy, electric current, which is represented by the capital letter I, is the actual water physically moving through the plumbing of a house. Without this movement, literally nothing else matters. By definition, it's simply the flow of electric charge. That's it. It's just electrons moving along a path. And to measure how much of that charge is flowing past a given point, we use a specific unit called amperes, or amps for short, which you'll see denoted by the letter A.
So how do we actually calculate that flow mathematically? Well, this formula, I equals Q over T, is basically the beating heart of electric current. I want to pause just for a second to let this simple mathematical relationship sink in. It tells us that current is really just a ratio.
Let's break that formula down piece by piece so these variables are totally isolated and super easy to digest. I is our current, Q stands for the total charge, and that is measured in a unit called coulombs, and T, as you might have guessed, is simply time, measured in seconds. So when you look at I equals Q over T, you are literally just dividing the amount of charge by the number of seconds it took to flow by. It's a measure of speed and volume, kind of like measuring gallons per minute in a water pipe.
Moving right along to step 2, the push, Ohm's law. But here's a question for you. Water doesn't just flow through a flat pipe all on its own, does it? No, it needs a pump. In electricity, that pressure is governed by Ohm's law, V equals I times R. Now, what's really interesting about this is how it permanently locks 3 fundamental concepts together. It tells us that voltage equals current multiplied by resistance, and through a little simple algebra, you can flip it around, like R equals V divided by I. The real beauty here is that if you know any 2 of these variables, you can instantly find the third. To keep things perfectly organized, let's just map out this relationship. V is voltage, measured in volts. This is the push or the pressure in our water pipe analogy. I is current, measured in amperes, that's the flow, and R is resistance, measured in ohms, which is the obstacle. So voltage pushes, resistance fights back, and current is the flow that actually makes it through.
Which perfectly sets up step 3, the obstacle, resistance.
You might be wondering, why doesn't electricity just rush through a wire at infinite speed? Well, that's because of resistance, represented by R. It is the active opposition to the flow of current. Imagine taking our water pipe and physically squeezing it in the middle. The tighter it squeeze, the harder it is for the water to get through, right? In an electrical circuit, certain materials or components naturally squeeze that flow of electrons.
But resistance isn't just some random number pulled out of thin air. It's actually determined by the physical properties of the wire itself. The formula is R equals resistivity times length, all divided by area.
Let's explicitly define these physical variables so we know exactly what we're looking at. The first variable, represented by the Greek letter rho, or noted sometimes as P for resistivity, is the natural resistance of the specific material you're using, so copper is very different from rubber, for instance. L is the length of the wire. The longer the wire, the further the electrons have to travel, which simply means more resistance. And A is the cross-sectional area, basically the thickness of the wire. A thicker wire is exactly like a wider pipe. It actually lowers the resistance because there's just more room for the current to flow.
Okay, on to step 4, the pathways, circuit types. Now that we've defined the individual components, the flow, the push, and the obstacle, let's shift our focus to the actual physical pathways they travel on, because how we arrange our obstacles fundamentally changes the math. We have 2 primary circuit types to look at. In a series circuit, the components are placed in a single line, one right after the other. The total resistance there is straightforward addition. R total equals R1 plus R2 plus R3. But in a parallel circuit, the path actually splits into multiple branches. Notice the very unique fractional math used here. 1 over R total equals 1 over R1 plus 1 over R3. Since the current has multiple paths it can take, adding more branches in parallel actually reduces the total resistance of the whole circuit.
Let's move to our final step and see how this all builds up. Step 5. The result: power, energy, and heat.
Once we have a flow that is being pushed through a resistance over a pathway, the electricity actually does something for us in the real world. First up, electric power. We can cleanly define power as the rate at which electrical work is done, basically work divided by time. This completely cements the watt as our core unit. So whenever you buy a light bulb or a new appliance, you're always looking at its wattage. It tells you exactly how much power that device demands.
And because of how beautifully Ohm's law interconnects voltage, current, and resistance, we actually have 3 different ways to calculate this power. P equals V times I, P equals I squared times R, and P equals V squared divided by R. It's super handy. Depending on which variables you already know, you just pick the corresponding formula to find your wattage.
Let's look at the ultimate final outputs here. Electrical energy is simply power multiplied by time, literally just how long you run that appliance. That gives us formulas like E equals P times T. Crucially, notice the incredibly practical unit here, the kilowatt hour. That is exactly what shows up on your monthly utility bill. And as a direct byproduct of this energy pushing through resistance, we get heat. Heat equals I squared times R times T. That right there is the exact math of why your toaster gets hot or why your laptop charger warms up when it's plugged in.
I want to leave you with this final thought. Knowing exactly how voltage pushes current through resistance to create power and heat, how are these invisible, powerful formulas interacting right now in the very device you are holding or sitting in front of to watch this explainer? Every swipe, every pixel, every sound is running on the exact math we just decoded together. Pretty amazing, right? Thank you so much for joining me, and stay curious.